All right, so last week we were working on acceleration, okay, which was any change in velocity. It looked like you guys were having zero problems with that. So we're going to move on here to work and energy. Work energy theorem is, in my opinion, and the opinion of most people who do physics, the most important concept in high school science. Okay, reason for that is it explains how everything gets done. Okay, work and energy have a very important relationship. Okay, energy is defined as the ability to do work. Okay, we learned that like the first day of this unit. So energy is the ability to do work. Okay, work is a transfer or a change in mechanical energy. So if I don't have energy, I can't do any work. Everybody follow me there? Like I can't, push a wheelbarrow down the street. I can't dig a hole with a shovel, okay? Because I don't have any energy, and all of those things involve me transferring energy or doing work to something else. Everybody all right with that idea? Yeah? Okay. So you can't do work, okay, if you don't have energy, okay? That's essentially the work energy theorem. We write the work energy theorem like this. Work equals delta E. Okay? Delta means change. All right? And anytime we have delta, what we're really saying is this. Final minus initial. Okay? So the work energy theorem says that work is a change in energy. Therefore, we subtract final minus initial, okay, to get our change in energy. All right. The other way that we can write work is with its own formula. Okay? Work gets done when you exert a force through a distance. Okay? So we can say that force times distance equals a change in mechanical energy. Right? That's where we get that from. That's the work energy theorem. Now, in order for work to get done, energy's got to change. There has to be a force, and it has to be exerted through a distance. So if I push on the board, okay, it's not going to go anywhere. Okay, if I push on the board, okay, and I push as hard as I can, am I exerting a force? Okay. Am I doing any work? Why not? Right. I'm not changing the energy of the board. It's not going anywhere. I'm not making it get higher off the ground. I'm not making it go faster. I am not changing its potential energy. I'm not changing its kinetic energy. I'm not doing any work. Here's the weird thing. Why do I get tired then? Yes, exactly. I have to brace myself against the force that the wall will exert back on me. That's Newton's third law. Every action is an equal and opposite reaction. Okay, when I push on the wall pushes back. In order to keep me from just doing this, okay, just coming off the wall because of the force the wall exerts on me, I have to brace myself, which means I'm using a lot of my muscles just to keep myself in one place. That's why I get tired. It's not because I'm transferring energy to the wall. It's because the wall is pushing back on me and I have to make sure I don't go anywhere. Okay, so in the end, I do lose some energy, but it's more like thermal energy. I just get hot and sweaty because I'm pushing on the wall and it's not going anywhere and that kind of stuff. Okay. All right. So work energy theorem states that work and energy can be equal, but one cannot exist without the other. And that's what we just said here. Work is equal to a change in mechanical energy. Okay. We need to understand the difference between kinetic and potential energy, which we've sort of talked about. We'll go into a little more detail and understand the relationship between force and work. That's this. Okay. That work is force times distance. So if I exert a greater force, will I do more work? Yes, yeah, provided it's moving, right? Okay, if I exert the same force, but I exert it over twice as much distance, I will have done twice as much work. Okay, that's the relationship between force, distance, and work. Okay, so energy, okay, is a measurable quantity. Okay, it's a measure of an object or capacities, or an object or system's capacity or ability to do work. Okay, right now, can this mousetrap do work? Yes, it can. Okay, this mousetrap is loaded. All right, the killing bar, that's this thing, okay, that's what it's called, okay, because that's what it does, that's its job, okay, is right now being held in place, okay, by the locking mechanism here, and this is the trigger, the part the mouse steps on, okay, where you put the cheese or the peanut butter, okay, is the trigger. So when they step on that, then the locking mechanism releases, and then the killing bar, boom, comes over, right, and snaps their neck. It sounds awful, but it's like the most humane way. It's way more humane than poison. Okay, and poisoning a mouse, yeah, it's a long and painful death. So this is much quicker. But the big thing here is that there is energy in this mouse trap right now. Okay, and there's energy in it because there's a spring, right? And in loading the bar, okay, we bend or change the shape of the spring. We exert a force on that spring by moving the bar over, okay, to the other side. We exert a force through a distance. That's us doing work. That puts potential energy, elastic potential energy in this case, into the mousetrap system. Okay, that energy can be released, and then it will do work. That work will be changing the shape of a mouse. Okay. All right, but that's essentially what it does. I mean, it's a very simple mechanism, but it shows exactly how work and energy are related. If I do not load that mousetrap by doing work on it, it has no ability to do anything. It's completely useless. All right, everybody all right with that idea? Okay. All right, so work is the transfer of energy, okay, from one object or system to another, and we're going to be specific here. This energy is mechanical energy. Okay, and mechanical energy is kinetic and potential. It's the sum of them. All right, so if I change the potential energy of something, I've changed its mechanical energy, I've done work. If I change the kinetic energy of something, I've changed its mechanical energy, I've done work. If I change both, same thing. Okay, I've done work because I've changed the mechanical energy of that object or system. Okay, and that can be as simple as I pick up this calculator. Okay, I picked it up, and now it has what kind of energy? Potential, right? Because I did work. Okay, it didn't have any potential energy here. Well, actually, it could, because it could fall off. But okay, right now it really doesn't have any because it can't fall. It's on the top of the desk. But if I move it to here, now it does have potential energy. Okay, it could fall back down to the desk, or now it could fall even further, right? So in which case does it have more potential energy? Yeah, when it's over the floor, it could fall farther then. Okay, so it would do more work. Okay, but the only reason it's got energy is because I lifted it to this height. Okay, I transferred that energy to it. Right, burning calories, lifting calculators. Okay, doing that kind of stuff. Okay. All right, so if you hit a tennis ball with a racket, you're doing work. Okay, you're exerting a force through a distance. Now, in terms of the speed of your serve, okay, the speed of your serve is dependent on essentially two things. How strong you are, okay, which is the force you can exert, and your technique. The better your technique, the greater the distance over which you will exert your force. Okay, so if you look kind of at this picture here, you can see, it's all kind of stop motion, but you can see that here, when the tennis ball and the tennis racket would hit each other right here, okay, will the ball go into the racket? Like if I'm looking at the racket, so here's the frame of the racket, okay, and the strings, are they somewhat elastic? Yeah, okay, so they're going to kind of bend like this, and the ball will actually be behind the frame, okay, when I hit it. Okay, having that elastic string helps me to increase the speed of my serve in two ways. First off, well, actually more than two ways. First off, it makes the racket lighter, so I can swing it faster. Okay. Secondly, it allows the ball to go back into the racket, which means I'm in contact with the ball for a longer period of time and thus a greater distance. Okay. The greater the distance over which I can exert my force, the faster I can hit the ball. Okay. If that is just a paddle, okay, I am not going to hit the ball as well. I'm not going to hit it as fast because I won't be able to swing it as fast, and the ball will hit the paddle and bounce off right away. I won't get that extra distance over which I can exert the force. Baseball has done absolutely nothing in terms of developing the science of sport in terms of physics. A Louisville Slugger is still a hunk of tree, okay, and a baseball is still a hunk of horsehide, okay. Like they really haven't changed that part of it in so much as, well, their argument is they're trying to maintain the purity of the game, which I think is ridiculous because the part of sports science they have embraced is this part. Right? That's why we got a bunch of roid monkeys playing baseball. Hey, sorry, that was out loud. Sorry, that was supposed to stay inside my head. But yeah, they have not really embraced the physics part of sports science very much in terms of that, because it means in terms of that it's a simple game. You hit the ball, right? Most other sports have gone the direction of improve the equipment because that will improve that'll improve the sport. Like if you look at hockey, for example, okay. When I was a kid, a hockey stick was a chunk of tree, okay? And wood is somewhat flexible, but it's nothing like the composite sticks they have now, okay? A hunk of tree, okay, would maybe flex, maybe let's say like this much, okay? So you'd have that distance over which you'd be in contact with the puck. But a modern composite stick is far more flexible, which increases the distance over which I can be in contact with the puck. And I get the extra benefit of an elastic potential energy stored in the stick because it's going to snap forwards when I'm near the end. So yeah, people are going to shoot, especially wrist shots, way faster today than they would have back in the day. Slap shots is not as big a deal, but wrist shots especially, like you see people lean on those sticks and it's practically 90 degrees, okay? But they do have a drawback in that if they get any nick on them, right, they shatter. Okay? And you've seen like there's been lots of games that have been decided because somebody wound up for the one timer and the stick just exploded. Okay, they didn't get anything on the shot. But yeah, that's sports science, right? That's using work energy theorem to an advantage. Golf has gone a similar direction. They've made all the clubs way lighter. They've made the ball a lot different, okay? Like 20, 30 years ago, a ball was like hitting a rock. It was solid, okay? Now they're flexible, they smash and they flatten against the face of the club, so they stay against the face of the club for a longer period of time, meaning you can exert that force for a greater distance and thus hit the ball much, much farther. Okay, people hit the ball now, it's like 75% farther than 30 years ago. Okay, like they've had to alter PGA golf courses by adding tee boxes because the courses were not challenging enough anymore. Okay, you know, they had par fours that were 400 yards long. Guys were driving the green, right? So they had to change things in order to, because the technology, the equipment just gets better. Okay, and we improve equipment by looking at physics. Okay, we look at work energy theorem. How can we harness the strength of the people that are using this equipment and get it back, you know, into the ball or into the whatever, okay, better or more efficiently. Okay, and tennis obviously is another one. Okay, better equipment. Tennis rackets aren't made out of wood; they're made out of graphite and composite materials, so they're lighter. Oh yeah, you definitely wouldn't want to drive to the game. You get a ball in the windshield every single time. Yeah. Yeah. Well, and that's why they don't let them use aluminum bats in the big leagues and things like that, right? It's just, yeah, better energy transfer and stuff. So, and really, like, there's not much you can do without really significantly altering the game in baseball to change either the ball or the bat. Right? It would significantly alter the game, like you say, 700-yard home runs, right? Like, yeah. Okay. All right, the big thing here, guys, is that we get more energy transferred if we alter either one of these parts of the equation. Okay, if we can increase the distance over which we do the work, we increase the work. If we increase the force we use to do the work, we do more work. Okay, and obviously increasing the force is also a big part of it. Okay, I mean, you guys as a generation have way better sport training than I did when I was a kid. Okay, I mean, we didn't know, you know, about injury prevention and how to be efficient and how to, you know, work different muscle groups. You always focused on the one sport, and that led to overuse injuries. And you guys, you know, you guys just have way better scientific background around developing your muscles. Okay, and of course, way better research into technique as well. But, yeah. All right, everyone okay with that idea? Yeah. All right. Okay, so work is related also to the force acting on the object. The greater the force, the more work is done. That's a directly proportional or linear relationship. If I double the force, I double the amount of work. If I triple the force, I triple the amount of work. Okay, mass can also affect the amount of work done because more or heavier objects, it's not so much, sorry, I shouldn't say it that way. It doesn't affect the amount of work done. It will affect the appearance of that work. Okay, if, for example, I think I have a picture over here on the next slide. We'll talk about it in a sec. So a bow and arrow is a very classic work energy theorem example. Okay, when you draw back the bow, are you exerting a force over a distance? Okay, does that store energy in the bow? Yeah, because the bow wants to go back to its original shape. Okay, and so when you release the string, all of the energy that you put into the bow will now be transferred through the bow into the arrow. Okay, and that will increase the kinetic energy of the arrow. Okay, in fact, it'll give it basically all to it. If it's 100% efficient, all of the energy would go into the arrow, and the arrow flies out of the bow at a high rate of speed. Okay, the bow and arrow is going to be one that we see over and over again. Slingshots, things like that are all classic examples of work energy theorem. You do work, it transfers to something else. Okay, so this is the example here that I was talking about. So I've got this guy with a golf club. Okay, in the first situation, he is using the golf club in the proper fashion. He's going to hit a golf ball with it. Okay, so he winds up and swings as hard as he can. Okay, he uses all the force he is capable of exerting. And he's exerting that force on a really, really small mass, the golf ball. So he's going to produce a very, very large what? A very, very large acceleration. Okay, massive because he's hitting a very small mass. Okay, in the second situation, for some reason, he's going to wind up as hard as he can, exactly the same amount of force, and he's going to smoke this truck. Okay, maybe, I don't know. He's going to hit the truck for whatever reason. Okay, now in the perfect physical world, if there was no friction, whatever, would the truck move? Yes. Yeah, if it was on a perfectly frictionless surface and I wound up and hit it as hard as I could with a golf club, it would move. Okay? It would produce an acceleration. In the real world, it still does. It still produces an acceleration. It's just we don't see the truck move. Okay, but the truck moves. If I'm standing out here at the front and I've got my hand on the truck, okay, and let's say blasting my music with my headphones and I can't hear anything, do I still know when he hits the truck? Why? I can feel it. The only reason I can feel it is because every single particle that makes up the truck moved. Okay, that force, the energy, the work that he did transferred through the truck. Okay, I can hear it. All right, the same amount of work is done in both situations, but it looks different. Okay, it looks different because the masses are different, right? But the same amount of energy would be transferred to both. Okay, but we would obviously change the kinetic, or we would see a greater change in velocity or greater acceleration for this ball than we would for this truck, but they would both receive the same amount of energy. Now, if this truck doesn't move, what evidence do I have that work was done? Well, I have the sound, right? It would make sound when he hits the truck. There's a vibration. All the particles in the truck vibrate and move that way. The truck doesn't roll or slide, but okay, they move. And at the end, has he changed the shape of the truck? Yes. Yeah, there'll be a dent wherever he hit it. That counts, okay? If you change the shape of something, you've done work on it. We just said a few minutes ago, looking at the mouse trap, that the work it was going to do was change the shape of the mouse. Okay, changing the shape of something means you've moved at least some part of it. You've moved that much mass, you've changed its shape. Okay, that counts as work. So in either case, I do the same amount of work, but it looks different because of the masses involved. Okay, everybody all right with that? Right. Okay, so motion doesn't just mean the movement of an object. It can mean a change in shape. When you stretch or compress a spring, okay, you're doing work. You're changing the mechanical energy of that spring. Okay, if you compress or stretch it, what does the spring want to do? right? It wants to go back to its original shape. That means you have put potential energy into it. And the only way to put energy into something is to do work. Okay, so even changing the shape of something is doing work. Okay, and that's the case with a spring. In this condition, the spring is at what we would say is, or what we would call static. It doesn't have any energy in this condition. This is the shape of the spring. If I alter that shape by compressing it or I pull it apart, okay, then it's going to want to go back. I've done work. I've exerted a force through a distance, made the spring longer or shorter, and it now has potential energy. Okay, so changes in the shape of an object constitute an exertion of force and thus result in work and energy transfer. So it's important to know, okay, that something doesn't necessarily have to move, okay, or change speed to have had work done on it. Okay, as long as its shape changes, it's got energy. Okay, questions on that idea? Okay. Now, work and heat are both transfers of energy. Okay, we talked about that the very first day. Okay, work, we said, is a transfer or a change in mechanical energy. Heat is which kind? Heat's transferring thermal energy. Okay, so they're similar in that way. They're both transfers of energy, but they're transferring different kinds. We're going to be dealing with just this. Okay, just the work. Right. Now, that doesn't mean, obviously, that moving particles, okay, thermal energy, can't be used to do mechanical work. Okay, we know that. We use it all the time. It's just not an efficient way to do work. Okay, when we burn fuel in our car, we talked about this a while back, but when you burn fuel in your car, okay, you cause the expansion of gases, okay, and that expansion of gases is the result of thermal energy, but it can be harnessed to do mechanical work. It can move a piston up and down, okay, things like that. All right, so potential energy is energy due to position or condition. So there's actually two kinds. We're going to be focused mainly on gravitational potential energy. Okay, there is elastic potential energy, but we don't get into that until physics 20. Okay, that would be the energy stored in a bow and arrow, the energy stored in a spring, or something like that. It involves a different formula that we don't use. Okay, in science 10 anyway. All right, you need to understand what elastic potential energy is, but you won't have to do any calculating to do with its formula. Okay, you will have to do a fair amount of calculating with the with the gravitational potential energy formula. All right, so how do I make sure that something has gravitational potential energy? Exactly, it's got to be above ground level. It has to be able to fall. Okay, the only way for something to have gravitational potential energy is if it has the potential to fall. Okay, so the first part of it then would be height. Okay, the first part of gravitational potential energy would be height. Now, what causes something to fall? Yeah, so gravity is part of it too. Okay, if there was not some force that would be accelerating the object, it wouldn't matter. Okay, I mean, if I'm out in interstellar space, I put something out in front of me, it's just going to stay there. It doesn't have any gravitational potential energy, right? What's the last thing you suppose could affect something's potential energy? Mass. Okay, think about it this way. You're walking down the sidewalk and two objects fall off of a building. One is a feather, the other is a piano. Okay, you're going to get hit by one of them. You have to choose. Most of us would stand under the feather, okay, because the feather has way less mass, okay, way less mass. So these are the things that cause, okay, or that affect, sorry, potential energy. All right, now, most people, when I bring up the feather example, they also say, but yeah, but Mr. Coderre, like a feather also does this when it falls, so it won't be going nearly as fast. That's also true in the real world. if we were operating in the perfect physical world, all things fall at exactly the same rate, at 9.81 meters per second squared. Okay? And it looks weird when you see a feather do that, because we all expect a piece of paper or a feather to do this, okay? But they don't always. I'm going to show you, I've got a video of it here. So all things fall at the same rate, okay? That's why this formula of gravitational potential energy equals m times g times h works, okay? Because g is the same for all objects, right? The only things that really can change the amount of potential energy something has are how big it is, its mass, and how high it's falling from, right? Obviously, the farther it falls, the faster it'll be going when it hits the ground, and the more energy it'll have as a result, okay? Everybody all right with that idea? Okay. Now remember, gravity does not work like in Looney Tunes. Okay, like where Wile E. Coyote runs off the end of the cliff and then doesn't fall until the Roadrunner points out to him that he's no longer standing on the cliff. Okay, it's just gravity. Gravity pulls you. Okay, and as a result, you are attracted to the Earth. Okay. All right. Now, so gravitational potential energy is the potential energy of an object due to its position. Okay, so where it is in relation to ground level, or the lowest point it could reach. Okay. All forms of potential energy must be described with respect to a chosen reference point. Okay, so if I was looking at this ramp, my reference points would probably be ground level and the top of the ramp. Right? If I'm looking at this diagram here, okay, we're saying that this is the lowest point, okay, ground level, that would be our reference point. Everything would be measured from there. Okay. All right, in the diagram on the left, the person on the left lifts this block to the top of the ramp. This person pushes it up the ramp. Who does more work? It's the same. Okay, they both do the same amount of work. Remember, here's our formula. M times G times H. These rocks have the same mass, and regardless of how they get to this point, they will have the same height when they get there. Thus, it takes the same amount of work to push something up a ramp as it does to lift it to the top of the ramp. That's the whole purpose of a ramp. Okay? Remember, we just talked about this a minute ago. We said work equals force times distance. Okay? Who goes the shortest distance? The guy lifting. This distance here is shorter than the ramp. Agreed? But does he have to exert more force? Yeah, because he's lifting it directly, right? The ramp isn't supporting any of the weight, right? So he exerts a greater force over a smaller distance. She exerts a smaller force over a greater distance. And as a result, they do the same amount of work. Okay, so a ramp, okay, which is the simplest tool, an inclined plane, okay, doesn't make less work. It makes work easier by allowing us to use less force over a greater distance. Okay, that's how inclined planes or ramps work. Okay, it's how the Egyptians built the pyramids. They didn't have help from aliens. Okay, they used sand to build really, really long ramps, and then had access to millions of slaves. Okay, it's a very efficient way to move really big bricks, okay, and make big pyramids, is to build really, really, really big, long ramps and have lots of people pull stuff. Okay, so that's the whole purpose behind a ramp. You need to understand the purpose behind a ramp. If you do not, you will be an inclined plane wrapped around an axis. Screwed. That's what an inclined plane wrapped around an axis is, a screw. Okay? That's why screws work the way they do. Okay? They're easier to put into wood than a nail because it's the inclined plane. Okay? They won't come out either. There's a greater force to pull them out. Yeah. Anyway, it's a Sheldon Cooper joke. I won't take credit for that one. If you watch Big Bang Theory, that's his joke. All right, so we can calculate the gravitational potential energy of an object with this formula. That formula is on your formula sheet. Okay, EP equals M times G times H. Okay, where potential energy is the gravitational potential energy of the object. The units for energy are joules. Important that we remember that. Okay, M is the object's mass in kilograms. Right? In this unit, we'll always be using kilograms for mass. In physics, we go big. Okay, so we use kilograms. G is the acceleration due to gravity, which, unless you're told otherwise, is 9.81 meters per second squared. Okay, and H is the object's height above the ground in meters. Right, so our units always have to be meters, kilograms, and joules. Right, so that we end up with the right stuff. Okay, everyone all right with that idea? Good. All right, so if I have a simple example here of a problem to do with gravitational potential energy. I have a 3 kilogram box lifted by an upward force 1.5 meters above the surface of the Earth to the top of a table. What is the potential energy of the box in its new position? Right. So what they give me in that question is the mass. They told me it's 3 kilograms. They told me the height, 1.5 meters, and they said Earth. Even if they don't say Earth, unless they specify a different value for little g, okay, it will be 9.81 meters per second squared. Okay, all I have to do is plug that into this formula. So 3 kilograms times 9.81 times 1.5 meters, and I get 44.1 joules. Okay, so that object would have the ability to do 44.1 joules of work, okay, from that position. What do you mean by we don't have to change? Plug it in to the equation, like we have 3 kilograms. Like that stuff, do we have to change? Not unless they give you the mass in grams or they give you the height in centimeters. Then yes, you have to convert it to kilograms and to meters. But I think you were also kind of asking this. Well, how do I get to joules? Yeah. Okay, so joules are not a fundamental unit. Okay, joules are a combination. The units for a joule are a kilogram meter per second, meter squared per second squared. That's a joule. Okay, because we're multiplying kilograms by meters per second squared by meters. So a joule is a kilogram meter squared per second squared. Never write it that way. Okay, it's a joule. Okay, that's why we write it that way, because it's thankfully mercifully less work. Okay, yeah. All right. What? Yes, kilogram meter squared per second squared, but no one ever says that. We just say joules. Okay. All right. Second example here. If I got a diver standing on a diving platform, okay, they have 5,400 joules worth of energy. So our givens are, they tell us the potential energy, 5,400 joules. That's 5.4 times 10 to the 3. Whoop, that's supposed to be a J, not a 0. That's terrible. Okay. We know that they have a mass of 55 kilograms. And again, we're assuming that this is happening on Earth because we're not told otherwise, where G is 9.81 meters per second squared. So we are looking for the height. So I've got to manipulate this formula for H. Is that going to be a pretty easy manipulation? Yeah, everything's being multiplied. So to leave H by itself, what do I do with M and G? Just divide them over. Okay, so my final formula here will be EP divided by M times G equals H, right? I just divide both sides by mg, comes over here. Everyone all right with that? Okay, so when we plug in our numbers here, we got 5,400 joules, okay, divided by 55 times 9.81. Now here's the thing though you got to be aware of. Okay, doesn't show that in the formula, but if you do not put that in brackets on your calculator will perform order of operations and it will not give you the same answer. Okay, so make sure you do the bottom operation and divide by that total number. Okay, then you will get a height of 10 meters. So this person is on the 10-meter platform. Anyone ever jump off the 10-meter platform? Yeah, it takes a while to hit the water. Like you're falling, like it's yeah, a little bit freaky. It's well more than a second of flight, okay, to fall from the 10-meter platform. And boy, you better be like a pencil, because if you got your arms out, it's like 1,000 hands slapping the bottom of your arm, okay, and you get the big red marks. Yeah, no, you don't want to be the belly flop champion, yeah, because you see those guys, they come on, they're just red, okay, because they enter the water the wrong way. All right. Okay, now kinetic energy is the energy that we see do work more often, but I'm going to give you about a 5-minute break here before I go into kinetic energy. Okay, so 5-minute break, then we're going to talk about kinetic energy. So if we're looking at kinetic energy is energy due to motion. So you only have kinetic energy if you're moving. And this is the energy that we see do work most often. Okay, because an object's moving and it slams into something else and it can do work, like a hammer pounding in a nail, okay, or things like that. Potential energy, like gravitational potential energy, actually won't do any mechanical work. It can be transferred or it can be changed into kinetic energy, but gravitational potential energy isn't going to do anything. My coffee cup has potential energy, but it's just potential. It can't do anything until I turn that potential into kinetic. Okay, then it can do work. All right. So I'm going to show you the guy breaking the sidewalk blocks, and then I'll show you. Well, actually, first I'll show you some guys breaking like wood, and then I'll show you the guy breaking the sidewalk blocks. Okay. A lot of it is technique, and a lot of it has to do with training. So as we were saying before, like if I'm going to use my hand to break like boards and stuff like that, I don't just walk up to a 2x4 and go, today's the day, and think I'm just going to go like this and snap a 2x4 or break a 2x4 with my fist. I'm just going to break my hand. Okay, those guys, what they do is they train on that stuff, on simple, on light stuff. They do a lot of impact things. They hurt in punching bags and stuff like that, because every time you do that, you create micro fractures in the bone. Okay, those microfractures are perfectly normal and they'll heal back stronger. That's why they tell elderly people who have osteoporosis to do a lot more walking. They do more walking, they create microfractures in their bones that increase their bone density and allow them to avoid hopefully breaking big bones like their hip or their femur or something like that. Okay, so you can increase your bone density by essentially making small breaks in the bone all the time. Yeah, muscle mass is similar in that like you break muscle fibers when you work out and they heal back bigger and stronger, right? A bone is the same, right? Except it's not fibers, you're creating small fractures that then calcify and heal and get more dense. Okay, so yeah, somebody who is like a boxer or a martial artist or something like that, they're going to have fairly dense bones in or fairly dense bones that they use to strike with. Okay, and you'll notice that most martial arts try to avoid striking with hands. Okay, if you look at like Muay Thai and things like that, there's a lot of elbows and forearms and knees and legs and stuff like that because those bones aren't going to break. Okay, they're more dense, they're heavier. Okay, hitting somebody with your hand, these are the smallest and the most delicate bones in your body. Okay, and even if you train regularly, you can break these, and you see that happen a lot actually in martial arts stuff. You see people break their hands all the time. No matter how much you train, these are still small bones. Right? They're not designed to do that. And that also accounts if you hit someone with the wrong part, right? When you hit someone with your fist, you want to hit them here, okay? But sometimes we miss, right? And you end up hitting them here or something like that. That's when you break your fingers, okay? Or you see people do this, okay? People who don't know what they're doing will clench a fist like this, put their thumb inside, and all that will do is dislocate your thumb, okay? You hit somebody like that and you're gonna pop your thumb right out, okay? Or snap it. One or the other. Okay. Same thing happens to stunt car drivers. Okay. It's not as big a work market anymore because they just CG most jumps now. But okay, back in the day when stunt drivers would jump a car, they would wrap their thumb over the top of the wheel and hold it like this. If they held it like you normally hold the steering wheel, when they land, they snap their thumbs. Okay. So these are the light bones, right? You want to use the more dense bones. So when you're breaking stuff, okay, you either have to use the hardest part of your hand, which would be here, okay, or you use something else, elbow, okay, knees, something like that. So big thing here, guys, is that when it comes right down to it, work gets done when something is moving and smashes into something else. Okay, we got to have kinetic energy for that to happen. Okay, so any moving object has kinetic energy. Okay, so when a solid object moves, all of the particles move in unison. Okay, we talked about that with the example where the guy hit the truck with the golf club. Okay, in that case, not all of the particles moved in unison. They all moved, but they moved kind of randomly, and the vibration was felt through the truck as opposed to the whole truck moved together. Okay, kinetic energy So even when molecules are not physically attached to each other, they can still move together, like wind. Okay, and we can see that wind can do a lot of damage. Okay, if you get enough air moving, that can be a lot of mass. Okay, air has mass. Like they said, they evacuated 30 tons of air out of that vacuum chamber that we watched. Okay, that's a huge amount of air. That's a lot of molecules. So there's an ability to do work there. From changes in temperature and pressure. Yeah, that's how it's created. Yeah, changes in temperature and pressure. Well, I mean, there's movement of the Earth as well, but no, it's mostly changes in temperature and pressure. Okay, now, things that can affect how much kinetic energy you have. Two objects are driving towards you at 50, well, let's be realistic, 20 kilometers an hour. Kid on a bicycle, bus. They're both moving at 20 kilometers an hour. And you have to step in front of one of them. Which one do you step in front of? The kid on the bike. Because what does he have less of? He has less mass. Okay. Well, yes, but still less mass, less ability to change your shape, okay, than the bus does by a fairly significant margin. Okay, I didn't say that though. One of them was going to hit you. Okay, and the other thing, there's only two things, guys, that affect the kinetic energy in an object, mass and speed. But here's the thing, the formula looks like this. Okay, this is how we calculate the kinetic energy of the object. 1/2 times the mass times the speed squared. So which of those two factors has a bigger effect on your amount of kinetic energy, your mass or your speed? Speed. Speed has an exponential relationship with your ability to do work, with your energy. Okay? If I double the speed of an object, it has 4 times as much kinetic energy. If I triple the speed of an object, it has 9 times as much kinetic energy. It is an exponential relationship, and that is something people do not understand. Okay, and we see it in people's driving behavior all the time. Okay, the place I'm thinking of most is a school zone. Okay, so what's the speed limit through a school zone? 30 kilometers per hour. Okay. So 30 kilometers per hour, okay, is okay, 8.3, repeating, meters per second. All right, so that's how fast you're supposed to go through a playground zone or a school zone. But we justify to ourselves that, you know what, if I go only 10 kilometers an hour over the speed limit, it isn't that big a deal. Okay? We tell ourselves that all the time. It's not that big a deal. It's only 10 kilometers an hour. Okay? Well, 10 kilometers an hour makes us going 40. Okay? 40 kilometers an hour is 11.1 meters per second. Now, I want you to compare the kinetic energy of this object versus the kinetic energy of this one. Okay, so if I'm driving, let's say, a 1,500 kilogram car, okay, that's going to look like this. 1/2 times 1,500 times 8.3 squared. Okay, that's how much kinetic energy a 1,500 kilogram car has going the speed limit through a playground zone, 52,083 joules. Okay, now I go only 25% faster. Okay, if I go 40, I'm only going 25% faster. Not that, well, it's actually like 30% faster, but okay, I'm not going that much faster, right? 10 kilometers an hour isn't that big a difference. All right, so 1/2 times 1500 times now 11.1 squared. Whoops, not an answer, entry. So I'm just going to change this now to 11.1. Nearly double. Okay, it's nearly double the energy. It's 92,592. Okay, nearly double the amount of kinetic energy, and I'm only going 10 kilometers an hour faster. Now, this is the scary part of it. In order to get rid of this energy, what do I have to do? Okay, how do I do that? I press the brake. The brakes will do work, or actually your kinetic energy of your car will do work on the brakes. They gradually wear out, the brake pads wear down, okay? But you're essentially doing work. You're turning this energy into heat. That's what your brakes do, okay? They take it from being kinetic energy that keeps you moving forward, and they turn it into heat and sound and even light. Sometimes they can glow a little bit, okay? You see it on race cars. If they're racing at night, you can actually see the brake rotors glowing like cherry red. Okay, but for the most part, it's just heat that they're producing. Okay, so work has to equal the change in the kinetic energy of the car. The brakes have to do enough work to take that number and make it 0, so that I stop before I hit a kid who runs out in front of me. Because that happens. Kids don't always pay attention. Okay, so the formula for work is force times distance. And I need to change my energy by 52,083 joules if I'm going the speed limit. Okay, so let's say that my brakes can exert 8,000 newtons worth of force. I'm just picking a number at random here, but 8,000 newtons worth of force. So F is 8,000 newtons. So if I calculate D, is that going to tell me how far I'll go before I stop? Yes. Okay, this is the distance. This is my stopping distance. So if I divide 52,083 joules by the stopping force my brakes can exert, that will give me the distance my car will travel at the speed limit before I stop. Okay, so 52,083 joules divided by 8,000 newtons worth of braking force. Going the speed limit, my car will still travel 6.5 meters before I stop. Okay, 6.5 meters is not quite the length of this room or width of this room. Okay, be maybe from that wall to probably about here. Okay, that's not too bad, right? You'd probably be able to react if a kid ran out in front of you, react in time, swerve, brake, okay, all that kind of stuff. All right. If I'm going 40 kilometers an hour, do I have a lot more energy to get rid of? What's going to happen to my stopping distance? A lot. It's going to go up exponentially, not linearly. Okay, this isn't twice as far to stop. This is way more than twice as far. Okay, or sorry, that might be about twice as far because it's not. I didn't go up by twice as much. I only went up by 30%. Right? I only increased my speed by 30%, but I'm going to increase my stopping distance by a factor of almost 2. Okay, that's a big deal. So if I'm looking at this same car, but now I have 92,592 joules worth of energy to get rid of using my puny 8,000 newtons worth of braking force. Right? Now it's 11 meters. Now it's this whole room and part of the hallway. Okay. But I'm only going 10 kilometers an hour faster. It's not that big a deal. Unless that's my kid. Then it's a big deal. Okay? That's what people don't understand. When they tell themselves and they justify to themselves in their mind that it's okay to go 10 kilometers an hour over the speed limit through a playground zone, they are saying they do not understand this. Here's the other part of that that's really awful. The average school zone is about 600 meters long, okay? About 600 meters. If I go through this at the speed limit, it'll take me 72 seconds. If I go through at 40 kilometers an hour instead of 30, I will save myself 18 whole seconds. So when you make that decision, understand what the reality of that decision is. You are saying that your 18 seconds are more important than that kid. Those 18 seconds could be the difference between me going home and having dinner with my kid or planning their funeral. That's 10 kilometers an hour. It's an exponential relationship, guys. And I've seen people do this. I've seen people go through playground zones and school zones at 60. Okay, at 60. This distance isn't 6.5. It's 4 times 6.5. It's like, okay, it's 36 meters instead of 6.5. Okay, at 60. That's huge. Okay, like 36 meters, like that's a long way. There's no way you'd ever stop if a kid ran out in front of you if you were going that fast through a playground zone. That's why playground zones have slower speed limits. Okay, it also means that, well, your ability, even if you didn't get on the brakes quick enough and you still hit somebody at the speed limit, you don't have as much ability to hurt them as you do if you're going 60. You have exponentially more ability to hurt them at that speed. And you're far more likely to do it because you can't stop as fast. Partially. Yeah. So then why is there like roads in the middle of nowhere that are like 30 kilometers an hour? Well, sometimes it's like condition of the road, right? Yeah, I don't know then. I mean, that's like out here, right? Like out here where it goes from 100 to 60 and there's nothing, right? Like there's really no safety concern, yet for some reason it goes from 100 to 60. I don't know. I mean, I think that should be 80 out there myself, but I don't get to make that decision, right? It's not like there's crosswalks or anything out there. I don't have to worry about little kids running across that road. Why is it 60? I don't know. Okay. No. They were out there the other day. But yeah, so that's the thing we got to think about, guys, is, okay, we got speed limits for a reason, okay? And part of it is just related to energy, okay? How quickly can you stop? What's your reaction time like? Okay, I mean, honestly, if this was based more on reaction time, playground zones, especially now, would be like 10 kilometers an hour, okay? Because man, oh man, do I see a lot of people who are not paying attention to the task at hand when they are driving, okay? It is rampant, but there are a lot of people texting and driving and doing whatever and driving, shaving and driving, doing their makeup and driving, whatever, doing lots of things other than paying attention to the road, okay? And that's a big deal, because part of whether you hit something or someone or not is how quickly you react, okay? I'm gonna demo this. I'm gonna use Alyssa as my guinea pig, okay? I want you to just put your hand at the edge of the desk. You're right-handed, right? Okay, just so you could like pinch this between your fingers. Okay, good. All right, so don't just open them up and be ready to catch it. I'm just gonna drop it, okay? Now, Alyssa's paying really close attention. Oh, sorry, put it the other way. Okay, she's paying really close attention. She's watching this thing. She's paying attention to the road, and boom, okay? So she caught it. It only fell 40 centimeters. Okay, take out your phone. And start doing something on your phone. That was actually pretty good. That's one of the best ones I've seen, but I didn't let her get too far into it. I've had this happen on this test before. I've had this happen on this test before. Oh! And guys, that's not far off, okay? It's not far off. People texting and driving, that's how unaware of their situation they are, okay? They missed a lot of stuff, okay? But you think about it, right? In the time it takes you to react, okay? In a normal reaction time, at the speed limit. You're going to travel 4 meters, 5 meters before you even react. Then you've got to, then you've got to process, apply the brakes, do your stopping. It adds up. If you're not even paying attention to the road, you don't react at all. Or you react so late that it's too late. Okay? In that way, texting and driving is worse. And I'm not saying that this is good, but it's worse than drinking and driving. You are actually more dangerous as a sober, distracted driver than you are as an impaired driver. Okay? Because an impaired driver will react. They'll react late, but they'll react. A distracted driver won't react until they hear the thump. Okay? That's why it's illegal. But people don't see it the same way, right? I mean, yes, there's still those people who are pathological drinkers and drivers or whatever and drivers, but okay, there are so many people out there who, oh yeah, I wouldn't text and drive, and the next minute they're on their phone not paying attention. Or they got the thing that sits their phone right in front of them, in front of the windshield, so they can watch TV on it while they drive. I've seen that too. Okay, like I saw a guy with an iPad on a mount to the windshield, and he was watching it while he drove. Okay, like it's boggles my mind. But how is that person watching that going to see a kid run across the street? But it doesn't. We don't have that ability to do that. Everyone go, oh, I can multitask. No, you can't. Okay? Driving is a singular task. All of your attention has to be on because it requires you to change your focus. Right? I got to check this mirror. I got to check that mirror. Look out. Okay? Look to the side. Shoulder check. You got to be doing that all the time. Right? If you take driver's ed, they tell you should be changing your view every how often? Every 3. Yeah, you should be looking all the time. I look to the mirror, look ahead. I check the mirror, look ahead, check my side mirror, right? That way, if you have to make a maneuver, you know whether there's somebody in either lane on either side of you. You know what's going on behind you. You know what's going on in front of you, okay? And you should be looking 15 seconds ahead, okay? That's how far ahead you should look. But you should change your gaze often. Every 5 seconds at the longest, you should be changing your gaze. What do you mean? To change your gaze?
Well, because if you're hauling a trailer, right, you're focused on, you don't check every 3 seconds, because that's just dumb, to check every now and then, just to make sure, because like when you're hauling long distance, right, it's generally flat.
I wouldn't go that far. I tow my trailer in a lot of crazy places, so.
Yeah. So if you check your mirror, you don't see it, right? You can drive and like, I don't know, 30 seconds later, you check again, still there, but you have to pay attention to your driving.
Well, I'm not saying that I would stare at the mirror. I'm just saying I look over. I look over, that's it. That's all I have to do. I'm not saying lock your gaze. I'm saying, okay, I check that mirror. That's it. I check that mirror and I'm back. Yeah, obviously most important is in front of you, right? But you still need to check that mirror, shoulder check. You got to do that. You got to be changing your gaze all the time because things change quickly. I think it's 5. I thought it was, back in the day when I took it, I thought it was 5. Look 15 seconds ahead and change your gaze every 5. But, okay, those are things, guys, there's reasons for that, right? And it has to do with how quickly you react, okay, how much energy you have due to how fast you're going. That's the reason they got the 50 kilometer an hour in the construction zones too, okay? Right. Well, the frustrating part of the construction zones is workers present. You drive 10 kilometers at 50 kilometers an hour. You haven't seen a single soul. And then you come up over the crest of a hill and there they finally are when you've finally gone, oh, they're not working, and you sped up, right? That's usually also where the police sit. Yeah. It would be nice if they moved the signs along with them, but yeah. Okay, so tomorrow we're going to talk more about kinetic energy. You will have a quiz tomorrow, and it'll be 2 acceleration problems. Okay, so I will post that later on today. Make sure you give that a try. Okay, your need for speed lab, don't forget, is due on the 16th. I mean, it's not far off. Make sure you're getting that done. Come in and asking for help if you need it. Okay.